Okay, so what's reaction rate and what changes it? That is the question, the essential question of this lesson. What is reaction rate and what impacts reaction rate? Last time we looked at signs of a chemical reaction. What is evidence that a chemical reaction is occurring? So now we're looking at what is reaction rate and what changes it, which is slightly different. So what's a chemical reaction again? Pause this video and tell the person next to you what a chemical reaction is. Okay. Hopefully you pause this video. Maybe the sub could have called on somebody, maybe, and asked somebody what is a chemical reaction. And you should say it's making new compounds or rearrangement of atoms, atoms making different bonds, something like that. Okay, what does this equation determine again? And what do the different parts of the equation mean? Again, pause the video and take, let's say, a minute and a half, 2 minutes, and tell the people next to you what does each part of the equation mean. Okay, so hopefully you paused the video and took 90 seconds, 2 minutes, and were able to answer what each part of this equation means. You should be able to say that this is the enthalpy change, and you should be able to say that a negative enthalpy means that energy is released from the chemicals, and a positive enthalpy means that energy is absorbed by the chemicals. And then here we have entropy. And so entropy is a measure of the number of possible arrangements, right? And then here we have the total energy change, or the Gibbs free energy. And so when we're talking about the total energy change of a reaction, that's what we're talking about. And you should also say which one determines if a reaction is favorable. Pause this video, ask the person next to you. Which one of these determines if a reaction is favorable? You should say that change in G determines if a reaction is favorable. That G, if it's negative, that means the reaction is favorable. And a negative change in H and a positive change in S are more likely to cause a negative delta G. Okay, so chemicals releasing energy and creating more entropy is generally favorable. Generally leads to a lower energy state. And remember, this equation considers the factors that determine whether a reaction will happen spontaneously without the input of extra energy. But that's different than saying how quickly it will happen. So a reaction might be quote-unquote spontaneous, spontaneous meaning it will happen without the input of additional energy, but it's not necessarily very quick. Okay, think about like a rock that degrades over time. You have a giant rock, and over thousands of years or more, it might break down into pieces of sand, right? Through wind erosion, things like that. We can call that a spontaneous process, where the entropy is increasing. There's more microstates at the end than there are at the beginning. But that doesn't mean the process is fast, okay? It's spontaneous, but it's not fast. So whether something will happen is different than if it will happen quickly, right? If you tell your teacher, if your teacher asks, when will you turn in that assignment? And you just say, oh, it will happen, it will happen, it will happen. Your teacher is not just concerned on if it will happen. They want to know how quickly it's going to happen, right? So reaction rate is the speed at which a chemical reaction converts reactants into products. And reaction rates vary exponentially. So sometimes it's like it doesn't happen at all. For example, industrial processes, sugar digestion, these are examples of, this is technically like the sugar, when you digest it in your body, technically without all the enzymes in your body that speed the process up, technically that process is still spontaneous. But if you put a piece of sugar on the table, That's a technically spontaneous process for the piece of sugar to break down into oxygen and carbon dioxide um, on the table there. But it's technically a spontaneous process for the piece of sugar to react with oxygen and release carbon dioxide and water just on the table there to combust. But it takes so long that that's kind of misleading because it would take so long, like we're talking more than your lifetime, for anything appreciable to happen. So it's basically not happening at all. To put exponential in mind, right? Let's say that let's pick someone in the class. Uh, Choose someone random in the class. The sub can pick a random name. Okay. Okay, sub picked the random name. So maybe we're in. Yeah, I'll let the sub choose random names. Okay. And so imagine that this student they get a magical puppy. So they're walking down the round point at Anmarist, and they see this guy, and he says, "Do you want a puppy?" And it's a magical puppy. And so your friend who's in the class says, "Sure, I'll take this magical puppy. Yes, I think a magical puppy would be nice." Be careful. He says the puppy will exponentially increase the population of itself. So you start with one puppy. You bring it home. Your parents say, okay. The next day, you come home from school. There's a second puppy. Now there's two puppies. You go back to school. The next day, you come home from school. There's four puppies. The next day, you come home from school. And in your house or apartment, there are 8 puppies. The next day, you come home from school. And there's 16 puppies. The next day, you come home from school. There's 32 puppies. The next day, you come home from school. There's 64 puppies. The next day, you come home from school, and in your house, there are 128 puppies. Parents aren't not too happy with this magical dog right now, right? The next day, you come home from school, 256 puppies, 612 puppies. It keeps going on and on. Finally, you find the magic man at the round point on Mount East, and you say, "I'm sorry, I didn't understand what exponential growth meant. If I knew that exponential was such a big deal, then I would have never taken these puppies in the first place. I'm sorry now." And then, because it's a story, you learn the power of friendship or something like that. And he takes the puppies back, right? And you don't have to deal with them. Exponential. There's a big difference, right, in rate. So reaction rates can vary exponentially. So a piece of sugar on the table is technically reacting with oxygen, but it happens exponentially faster in your body, okay? Because of the other chemicals in your body, or the enzymes in your body, that speed that reaction up. Without those enzymes, you would die because the reaction rate would be too slow. It's exponentially faster. It's way faster. It's a big deal. Okay? Another example is the ozone layer, and I'm not going to get into too much detail on this, but there are chemicals that are released into the ozone layer accidentally from Earth that act as catalysts that exponentially speed up the breakdown of ozone. And that is bad for us and the environment for various reasons that if you were to take physical science, you would learn. So let's talk about different ways that reaction rates can be sped up. We have type of substance. Some reactions between different compounds just occur faster than others. So some reactions are very quick. For example, sugar and sulfuric acid react faster than sugar and oxygen. Here are some factors that might take a single reaction and make it faster or slower. We have type of substance, concentration, temperature, phase and surface area effects, and a few others to talk about. Now, reaction rate depends on the amount of collisions of the atoms and the energy of the atoms. The more collisions, the more chances to react. Now, something you'd learn in AP Chem that I'll just mention 10 seconds here is that technically it's not just any collision. They have to collide with the right orientation or in the right direction so that the right atoms hit each other for them to react. But the more collisions, the more chances of reaction. And the higher the energy of the atoms, then the more likely they hit each other with enough force to react. Because if they don't have enough energy, if you recall from last lesson, activation energy, pause this video, pause this video, pause this video, pause this video, pause this video. After I ask this, tell the person next to you, what is activation energy? Pause this video, pause this video, pause this video, pause this video, pause this video. Okay, hopefully you were able to tell the person next to you activation energy is the energy of the transition state. It is that bump in the energy between the reactants and the products, and it takes energy to go from reactants to products. So the more energy the atoms have, the more likely they're to collide with enough energy to make that transition happen. If they don't collide with enough energy, the transition won't happen. And so the higher the temperature, then the more energy the particles have on average, and so the more likely they collide with enough energy to react. So make sure you understand that reaction rate depends on the amount of collisions and the energy of the atoms. Don't just say the first one. So we'll get back to this, but make sure you don't forget that the more energy the particles have, that also increases the reaction rate. Okay? So the more collisions, the more chances of reaction. I have a silly analogy for you. So, actually, my grandmother is a very, very proud woman right now because she pulled off every grandmother's dream. Every grandmother's dream. My father's side of the family is Catholic. My grandmother is Catholic, and I am the first in my generation on my father's side to have been married, but I'm also the oldest on my father's side. And now that I have like a bunch of cousins who are like 19, 18, 21, so they're like 10 years younger than me-ish. But then the next oldest, he's getting married next month, and I'll actually, surprisingly, probably be able to go to that. But my grandmother's super excited because she did what every grandmother wants to do. Grandmas are always like this. If you've ever seen Pride and Prejudice, there's this lady called Mrs. Bingley, and she's always trying to get her daughters to go to the dance because she thinks if her daughters go to the dance, they'll run into more people. Now, if we're talking about people, we're not literally talking about running into people, okay? Boys, if you're trying to get a date at the dance, you don't literally run into somebody to see if they'll go to the dance with you. That is probably not a good tactic. Don't literally run into them. If you haven't asked yet, you should ask them nicely. Just, say, hey, Sally, would you like to go to the dance with me? Although you should have already asked by now, but, so there you go. But you don't literally run into somebody to see if they'll go to the dance with you. But atoms will literally run into each other, and if they collide with enough energy, they react. That does not mean that if you want to go to the dance with somebody, gentlemen, that you should run at them very quickly to see if you collide with enough force with them in order to react. No, okay? But for atoms, that's the way it works. And so it's kind of like a mom or a grandma who's always trying to bring their daughter or their sibling and get them to meet people of the opposite gender. Because they think the more times they run into somebody, the more chances they'll react. Okay? So that's kind of a nice metaphor for you. And my grandmother's very happy because she, quote unquote, arranged this because she was the one who introduced this girl, went to her church, her Catholic church, her mass, and she introduced this girl to my cousin, and that's how they met, and that's how they're getting married. And so my grandmother is just absolutely beside herself with pride, as she should be, So, right, the more chances of collision, the more chances that the grandma's dream comes true. And so in terms of atoms, the more times they collide, and with the more energy, the more likely they react. But gentlemen, don't run into people in the hallway. hoping they'll go to dance with you. And it doesn't help your odds if you run into them quickly, but for atoms, it does. Okay, concentration. So, the next is concentration. The more concentrated the compounds that are reacting, the more collisions between particles, and so the quicker the reaction. Now, concentration means how many of the chemical per volume. So we could either be talking about volume of liquid, which means we're talking about aqueous, and then we're talking about something we'll learn soon, which is molarity. So how many moles per liter, aqueous, and then concentration is molarity. Or actually, it's also molarity if we're talking about a gas, because you don't think about it, but like a gas takes up space and has a certain concentration, right? You can imagine it's, like if someone farts next to you and you're outside in the air, say it's your little brother and he farts, but you guys are outside. I mean, come on, it's still your little brother. It's still annoying, but it's not that bad. But let's say you all get trapped in an elevator that's not opening, and then your brother rips a huge fart. I mean, that concentration's very high. That is going to be annoying, right? So that's the atoms or the particles per amount of space. Okay? So it could be a liquid or it could be gas. But the more particles per amount of space, the more likely they'll collide and react. Just like when your brother farts in the elevator, there's more particles reaching your nose than when it's in a larger space and is less concentrated. So the higher the concentration, the more likely they collide and react. So you can do an outside analogy. After I explain this, you could pause the video and do it, and then write the answer in your notes, and then share your answers with the people next to you. So for your outside analogy, you could go outside. You could pick an area and designate it like the basketball court, and then you could add people one by one to the basketball court and have them be moving around in the basketball court as you add them. And so as you're adding people, you are increasing the concentration. Now, you can spice it up. You can add one boy and one girl at a time and have people walk around with their eyes closed. And the boys can represent reactant A and the girls can represent reactant B. And the more the concentration of each, the more boys and girls, the more chemicals per volume, the more likely they'll run into each other, and then the more likely they react. Okay? So you can try that with the sub. Okay, so hopefully you tried that outside analogy with the sub. Now take like 90 seconds, 2 minutes, to write in your notes, what did you do, what did it represent, and you can go over it, and then the sub can call on somebody to answer what you did. Okay. There's a lot of people there. Quite a concentrated porta potty. I think you can look this up. I think there was like 50 people in that porta potty. So there you go. It's like a portable toilet. It's a cheap toilet that you can put like in a park. Don't do that. Okay, temperature. The greater the temperature, the more collisions of particles. So the greater the rate of reaction. Okay? So they collide more often because temperature is the random kinetic energy of the particles. Again, I don't know if have we talked about this yet? Temperature is random kinetic energy. Temperature is random kinetic energy. So the higher the temperature of the particles, the more random kinetic energy they have, the more they collide because they're moving more on average. And they collide with more energy. So there's additional energy supplied to break bonds of molecules, catalyzing reactions. So in other words, I would add this. They collide with more energy on average to overcome activation energy, okay? Because there needs to be enough energy of the particles for the activation energy to be overcome, right? Which is the energy of that transition state. So make sure if you're asked how does temperature impact reaction rate, there's two reasons. For some reason, students always forget the second reason. That second reason is just as important as the first reason. So make sure you list both. Because remember, it takes energy to break bonds. So if the particles don't collide with enough energy, there's no energy to break those bonds to get over the transition state. Okay? Yeah, sure, the new bonds that form will release energy, but the breaking bonds requires energy. And so that comes from the temperature, often of the particles themselves. Now, I'd like you to, after I make this explanation, pause this video and click on this video in the slides and watch on your Chromebooks this video about temperature. Then, once everyone's watched on your Chromebooks this video about temperature, you can answer the question, what is temperature versus heat, in your notes. So you should watch the video on temperature, and then you should take, let's say, 2 minutes to write in your notes and talk with the people next to you, 2 to 3 minutes after you watch the video, to write with the people next to you and write in your notes, what is temperature versus heat? Okay. So pause and do that. Pause, 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 pause. Okay, hopefully you did that. So you should say that temperature is a measure of the average kinetic energy, average random kinetic energy of the particles, versus heat is the total amount of energy. Okay? So again, temperature is an average. It doesn't matter if it's a swimming pool of 100 degrees Celsius water or a teapot of 100 degrees Celsius water. The temperature of those is the same. The heat is not, but the temperature is the same because temperature is an average. Okay? If you have a bunch of 6 foot tall men, like me, I'm basically exactly 6 feet tall, not super tall, not short, right? Just slightly above average. But 6 feet tall men, they're 6 feet tall. It doesn't matter if you have 10 of them or 10,000 of them, their height is 6 feet tall. It's independent of how many there are. And so temperature is like that. Temperature is a measure of the average energy of the particles. Okay, here's another outside analogy. I'm going to explain it, and then you can do it. And then once you do it, again, you can take 2 minutes to talk with the people next to you and explain it amongst yourselves, and then I can give you my explanation. So here's this outside analogy that you can do. So you can go outside, and you can have all the boys and girls as the reactants again in the basketball court or whatever area that you set aside, the petit plateau or whatever, and you have them moving. And at first you have them all moving very slow. And then you should have like 2/3 of the people move medium speed. And then you should have like 2/3 of the people move fast. Now, 1/3 of the people, 1/3 of the boys and 1/3 of the girls should keep moving slow the whole time. Designate that beforehand. Because this represents average. Because not all the particles have the same amount of energy. If you remember in the Boltzmann distribution where we had that curve of energy, there's an average amount of energy that the particles have. Okay? But not all the particles have the same energy. So for this outside analogy, keep 1/3 of the people moving slow to symbolize that some of the particles don't have more energy. But on average, they have more energy as the temperature goes up. And so you can have slow, medium, fast, where 2/3 of the particles start out slow. Everyone starts out slow. Then 2/3 of the particles move medium speed. Then 2/3 of the particle moves fast speed. And if some people are moving slightly faster than others, that's fine too, because there's some particles way up here at the most energy, but most are kind of in the middle, and that's how we get the average. The average is going to be somewhere around the hill, right? I didn't draw this exact, but you get the idea. So go ahead and do that, and then you can come back and answer the question. Okay, so pause, 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 pause. Okay, so hopefully you were able to answer the question. And so you should have said something that like it represents the average, and that individual particles have different speeds. But as the temperature increases, on average, the particles have more energy and they're moving faster. And so you should be able to say also that this means that they have more collisions, so more chances to react, and they collide with more energy, so more chance to have enough energy to overcome the activation energy and react. Okay, some other effects. Phase and surface area. The more surface area, the more collisions between particles, because there's more atoms exposed, so the greater the reaction rate. And this also deals with the transfer of heat too. So for example, like if you have shredded ice or a bunch of little pieces of ice, it makes the water colder faster than one ice cube. Same for a chemical reaction. If you had a metal reacting with an acid in a liquid and it was one block, it's going to react a lot slower than powder or little pieces of the metal. So the more surface area, the more total atoms that are exposed out of the material and the less that are like hidden inside. And so the greater the rate of reaction because the more collisions that are happening. Some miscellaneous effects. Pressure. If the pressure increases while the amount of particles remain constant, then if this is gases, if the pressure of gases increases, then you're effectively like increasing the concentration because you're giving the particles less space. So there's going to be more collisions because the gas particles have less space to move around. So they're going to collide more. Diffusion rates. In some liquids, the particles in the liquid spread out slower. So, for example, or a gas. So, for example, if a gas spreads out really quickly, then it's going to react with things in its path more quickly because it gets to them faster. So you can think about it like a firefighter, right? Firefighters diffuse quickly. They spread out quickly. Different gases or different things when you even stir them into a liquid are diffused or spread out at different rates. So something spreads out in a liquid or as a gas in the air, if they spread out faster, then they're going to be able to react with things that they come across faster because they reach them faster. So again, this could be particles in a liquid. If you just add them and they sit there and then they slowly spread out, like a dye, for example, you can picture like a dye in water. If you just drop a piece of dye, of color dye in water and slowly spreads out, that's the diffusion rate. The same thing can happen with like a gas in the air. So the faster the gas diffuses, the more likely or more quickly it will react with something. Stirring. We stir a lot in chemistry. Why do we stir? Stirring increases the kinetic energy of the particles in the solution, causing their collision rate to increase and increasing the reaction rate. And so the more stirring, the more the particles move, and so they hit each other and react. So same thing or similar thing, you're increasing the rate of solvation, which is the process of making a solution, when you add sugar to tea and you stir it. Or, if you're making a taya, right, you can like do the thing that they do in some parts of West Africa where you like go like this, right, and you pour it. That's kind of like stirring. You're mixing it, you're increasing the kinetic energy, increasing the collisions, which is going to cause it to dissolve faster. So that's not, sugar and tea, by the way, is not a reaction, it's dissolving, which is different, as we've talked about. But the rate of dissolving or the rate of a chemical reaction are increased by stirring. Solvents. If two things react, then both will react faster if they dissolve well in whatever it is. So if a solute does not dissolve well in a solvent, remember solute is the thing in a solvent, the thing dissolved in a solvent, so U in a V, solute in a solvent. If a solute does not dissolve well in a solvent, it will not react as much with other solutes in that solvent. So for example, you might know that oil doesn't mix well with water because oil is nonpolar and water is polar and can hydrogen bond, right? So we learned that like dissolves well with like. So polar dissolves well with water, oils do not. So if you had an oil and let's say there was something in the oil, a reactant in the oil, that's not going to react or mix with the water very much. Again, mixing and reacting are different things, but if it's not mixing with the water, it won't, let's say it can react with water molecules. Well, it's not going to react with the water molecules just if it doesn't get in physical contact with them. So if for things to react quickly, they must be able to mix well. So if they're in different solvents, they're not going to react very fast. And lastly, we have catalysts. All you need to know for general chemistry are that catalysts help a reaction to occur faster, but they are not reactants. Their atoms aren't changed. So sometimes in a chemical formula, we can have something like A plus B makes B plus C. B is a catalyst because it's not reacting. It's there at the beginning and the end. So it speeds up the reaction, but it's not reacting. Commonly in general chemistry, though, you'll see it written like this: B above the arrow, representing that B is needed to make the reaction occur quickly enough as a catalyst, but it's not actually reacting. So it speeds up the reaction, sometimes exponentially, from it's not occurring at all to now it's occurring really quickly, but it's not actually a reactant. And in biology, you probably learned about enzymes. Enzymes are biological catalysts. Without enzymes, we'd all be goners. Okay? Enzymes speed up the chemical reactions in the body, like the processes involved in cellular respiration that provide your cells energy to live. Those processes are occurring every second. Without enzymes, they would take too long and you wouldn't get energy and you would be a goner. Okay? So, those are the effects of reaction, things on reaction rate. And hopefully we can do some labs on signs of a chemical reaction and effects of reaction rate. Maybe next week on like Wednesday. I'll see with the sub, figure it out. But there you go. So I will ask that you then do what you did last time, and once you finish these notes, go over the outline questions and answer them and prepare for the quiz, which will be next class, because you should never stop learning. And who doesn't love quizzes? So there you go.